everyone. Today we're going to talk about measuring moisture in foods, and there's a lot of importance behind measuring moisture content in foods, and in many cases it's a regulatory requirement to be able to indicate how much moisture or how much solids content, conversely, is in a food product for sale. You can't just pump food full of water and sell it, because that's not giving good value to a consumer. And so in many cases, governments have set these standards. In other cases, companies need to understand the moisture content of a raw ingredient coming in so that they are having good quality control on incoming ingredient or outgoing product. So in this video, we're going to discuss why measuring moisture content or solids content is useful. We'll discuss the equipment necessary for doing it. We'll go ahead and do some of the math to evaluate the moisture content or solids content of products, and then we'll talk a little bit about some additional logistics and difficulties for measuring moisture in complex samples and troubleshoot some opportunities to overcome those challenges. So again, as I mentioned, some foods have illegal water content, and I say water versus moisture. Moisture and water are two different things, and I've got a slide coming up that explains it differently. But again, some products have standardized moisture contents that need to be obtained. So, for example, if you were a bakery, this is a classic one. Incoming flour is standardized to 14% moisture content consistently. And if you were a baker receiving flour in, let's say you were living somewhere really high humidity. Maybe you were in Vietnam, for example, with a high ambient relative humidity. That bread flour may not be at 14% moisture. It may be at 16% moisture. And this could be changing the formulation, the amount of water that you need to add to a formulation to be able to make quality bread. Or conversely, maybe you're somewhere extremely dry, or that moisture content could start to impact on the shelf stability of that product. So these measurements are extremely practical, and fortunately they're not too difficult to perform. So we also want to mention that solids content is sometimes the measure of note, and the methodology for measuring moisture versus solids, total solids in this case, is extremely similar. We are just using a slightly different mathematical approach. There are some other ways that solids are measured, for example, Brix content or so on, but we are measuring total solids, and this could be soluble or insoluble solids, and Brix is measuring soluble solids specifically. So in essence, let's say we've got some cheese here, and it needs to be let's say it needs to be 40% total solids, then we would assume that it is 60% moisture content in that cheese. The solids is what remains on evaporation of everything that's volatile in that sample, and the moisture is in essence everything that's volatile. So we just sort of summarize this. What does moisture mean? Why are we not saying water content? Well, I've got a little shot glass that's imaginary vodka here. Imagine that vodka was, let's say, 60% ethanol. If we were to measure the water content, well, it's 60% ethanol, well, it's 40% water, let's say. Well, if we were to perform the method that I'm going to describe for measuring moisture content, you'd end up with pretty much no residual, and it would all be gone. Moisture is not just water. It includes anything else that during the heating process that is used for measuring moisture content is going to evaporate off. So anything that is volatile, alcohols, esters, organic acids, anything that can evaporate off the sample during the heating process is going to be measured as moisture content. And so again, alcohol is not water, esters are not water. So we do not say water content, we say moisture content, and that generalizes anything volatile. So the method that's most commonly used for measuring moisture content is what's called a gravimetric method. And in essence, we're measuring uh, the mass of that product before and after heating to see how much a material is volatilized off. And we've talked about this before, that there are standardized methods in many cases. Moisture content does have standard methods, and some governments have standardized methods. AOAC official methods include methods for moisture content, but this is one method that is so much in the public use that in many cases companies don't even refer to a specific methodology unless their laboratory requires ISO 17025 certification and standardized methodology. So as a quick summary, you're going to have a lab oven. It's going to be preheated to just above 100 degrees Celsius. And the intent of that is that you are able to volatilize water off of that sample and other volatile components, and slightly above the boiling point, just in case there's bound water that's bound with colligative properties to a solute within that product. You've got some washed and oven-dried weighing pans. You don't want to have freshly washed it and then still have residual moisture on it. You want to have dried those pans, and not just with a paper towel or a hand towel, but dried in the oven specifically, so there's no residual moisture on those pans that you're artificially weighing. You're going to measure and the tare weight of that pan so that you know the weight of it, and you're able to, through marking or identification, identify the weight of that pan before and after the heating process. You're then going to weigh accurately a sample. Now, many of the AOAC methods say 5 grams. However, in certain cases, 5 grams of a sample is going to be a huge volume of sample, and it's not realistic. In other cases, 5 grams is extremely expensive. Here in Canada, for example, we have many food companies who are now doing research into the use of cannabis in food products, and 5 grams of cannabis is extremely expensive. Maybe you work in somewhere where spices or saffron are being analyzed, and 5 grams could be very prohibitive. So the main thing is to weigh accurately. The larger the sample size, the better the statistics, but also the larger the sample size, the larger the amount of mass transfer required. And therefore, 5 grams is the consensus for most food products. Transfer your pan to the oven. In many cases, you'll have a small lid to prevent dust from falling into the sample and being inaccurately weighed, also preventing drafts and during the handling, loss of the sample during that process. And so, but make sure to keep the lid cracked open. I've seen students try and measure the moisture on a sample and have the lid sealed up so tightly that the moisture can't actually be transferred off of that sample during the heating process. AOAC methods encourage you to dry for approximately 3 hours. Main thing is you've got to dry so that the weight becomes stable. And so you may find, depending on the type of substrates that you're working on routinely, that 3 hours is more than enough and it can be shortened. And in other cases, you might find that 3 hours isn't enough and you may require additional time. Main thing is we're drying it so that the weight is then stable and you do not see a change in weight with additional drying. Then we're going to take crucible tongs and transfer the pan out to the desiccator. There's a reason that we're using tongs to do this transfer. We don't want to be doing it with our bare fingers in particular, because the fingerprint oils and moisture from our fingertips can add to the weight of the pan. And if we're measuring using an analytical balance that's measuring down to milligram quantities, fingerprints can, or sweat, can add enough weight to throw off the validity of your sample. So we're using tongs or tweezers of some sort, so we're not physically touching the cup after it's been dried. Then we're going to transfer it to a desiccator for about an hour or two. Again, how long it requires is dependent on the quantity of samples that are being transferred over. I worked in a laboratory at one point in time where we do several hundred samples on any given day, and the mass of samples meant that we had to let it cool overnight because there was just so much thermal energy in the desiccators that it just required that much more time to dissipate. But you want it to cool down back to room temperature, and for a small number of samples, 1 to 2 hours is plenty. And then you're going to reweigh on the analytical balance. We have it in the desiccator because, again, depending on your location and depending on the relative humidity in the environment you're working in, and also depending on the sample characteristics, those samples, especially if they have humectant components in it, components that are going to absorb moisture out of the air, you could be getting reuptake of moisture in that sample and get an erroneous result. Having it in a desiccator means that you've got some sort of adsorbent material. So it could be silica gel, it could be a few different compounds that are used as desiccants that will absorb moisture out of the air and create a very, very low humidity environment in that chamber. Once we're ready to weigh the dry weight, we're going to transfer the sample out to the analytical balance and weigh it again, recording the value and making sure that we've noted the exact sample. Again, I mentioned I worked at a lab where we did hundreds of these samples in any given day, and it was so easy to mix up one sample with another. So do keep note of the sample code that you're working on. Then you're going to set up a sample recording sheet. And at this point, I'm going to flip over to my Excel because I want to show you some of the math that's involved. And in many labs, you'll have an actual printout, and in other places, you will enter your data directly into a computer using some sort of laboratory information management system. But there's some basic data collection that you want to do from a quality control perspective to organize your thoughts. So I am going to switch to my Excel at this point. So in our Excel document, I've just put some of the basics that a good quality control record is going to have. You have the name of your analyst, you have the date that you collected your data, you have the document that you're working from and the version code, and then from there we're collecting all the different pieces of information. I've got some imaginary information here, but let's say we're measuring the moisture content in all-purpose flour. Typically, you are going to do duplicates, possibly triplicates on that sample to make sure that there's that you have a representative sampling of that product. So I've got the tare weight of the pan, and I've recorded it here. Again, keep as many decimals as possible. As you recall, I mentioned we wanted to add 5 grams weighed accurately. And so I do not need to sit and agonize and say, well, I need it to be exactly 7.354. Main thing is I'm measuring it accurately and I will be able to adjust for that variation. Then I'm going to go through my experiment and I've got my dry weight in my pan. This is including the weight of the pan. And I want to make sure that I am recording, if I'm weighing out and recording the number with the weight of the pan, that it's very, very clear. I don't want any ambiguity that, do I need to delete the tare weight or do I not delete the tare weight? By making sure it's absolutely clear in my documentation, there's no confusion here. Then I'm going to subtract the tare weight from my pan. So you can see my math here. I'm going to repeat my math here. I'm going to take the wet weight minus the tare weight to get the wet weight with no pan included. And the same for the dry weight. So I'm going to take equals the dry weight with the pan minus the tare weight. Now, if I want to figure out my solids content, if I were to just take the dry weight over the wet weight, what I'm going to end up with is a percentage. If I multiply that by 100 to get out a percent, we note that the solids content is 85.99%. And so in essence, what do we have going on here? We have all of the stuff that volatilized off of this sample is disappeared into the atmosphere, and we're left with the solids content. Well, if we want the moisture content, it's everything that's disappeared from that original 100%. So we could take the solids content and 100% subtract the percent of solids to get our moisture content. So we could do it that way. Oops. So 100% minus the solids content gives us hey, you remember I said flour is often 14%. You also likely have watched other videos of mine and know that I often am manufacturing my numbers because I'm doing representational mathematics for you. But you can do your moisture content by doing direct subtraction, or you can do your moisture content by figuring out how much moisture weight was lost during the process. So let's just do that quickly here too. We can figure out that how much weight was lost during this process equals, so I'm going to take my wet weight, I'm going to bracket this, minus my dry weight. So now I have, in essence, the weight of moisture lost divided by my wet weight. Let's see if this gives us 14. Oh, I forgot to multiply by 100. Multiply by 100%, and we get out our number again. You can do this yourself, and I encourage you to build out a spreadsheet to be able to do the calculations. The nice thing is, once you've got the mathematics in there, you can copy and paste down an entire spreadsheet. And remember, I mentioned how I worked in a lab where we did hundreds of these samples on any given day. Well, all I had to do was my data entry, and then all the math fell out as soon as I copied and pasted those equations down. As I mentioned, some samples are slightly more difficult to manage, and there are a few other ways of dealing with measuring moisture content. So in certain food products, the moisture content just happens to be extremely low, such as in coffee or hard candies or dried fruits. The moisture content in many cases is bound up with the colligative properties of the different solutes within the product, and therefore the water is bound, in essence, to the food product and very difficult to pull off through the gravimetric method. And so we use a potentiometric method where iodine is being titrated and the potentiometry is being measured. Most Carl Fisher is now done using automated titration, and this perhaps will warrant a separate video at a later time. But be aware that not all products can be easily measured using gravimetric method. Some places use vacuum ovens or vacuum assist for doing the drying process, and this is where you're reducing the atmospheric pressure on that sample so that it increases the vaporization of anything volatile within that product. This is great for delicate samples. For example, I mentioned that many of the standard methods indicate the equipment that's necessary. Well, in the case of testing for moisture content in certain functional ingredients or additives or vaccines or chemicals used for animal health, they'll be using a vacuum oven because it's going to be less destructive to some of the biological chemicals in those samples. There are meters such as this Ohaus meter. Ohaus was one of the leaders in this technology, where you have an analytical balance and a heating element built into the same module. And so in essence, you put that foil cup onto a balance And then up here in the lid, there's an infrared heating element that goes through a cycling process of heating up the product in the pan, then letting it cool back down and weighing it. And it recirculates through that process of heating, cooling, and weighing until the weight doesn't change through a number of heating cycles. And so it's very convenient if you have one-off samples that need to be done. Otherwise, you need to have a bank of these. Again, if I had to do it with those 200 samples at the government lab where I was doing flour testing, I would have needed a whole bank of these. And these are convenient devices, but they are several $1,000s Canadian or American to purchase. The nice thing too, the math can be automatically done for you, and so this can become like a black box technology for a minimally trained worker to be able to perform. I have worked in countries where they say, well, that's great. I would love to do moisture content, but I don't have all the access to these fancy things. Well, there are ways to do bootstrap setups for moisture content using gravimetric methods. Main thing is you need a heat source. I've seen organizations use toaster ovens or small ovens that are going to give a consistent heat source that can be checked with a thermometer. They're going to be watching out for draftiness in this oven, so no convection ovens with a fan. You can use small foil cups or small steel pinch bowls that are available in kitchen supply stores. Main thing is avoid fingerprints, treat them the same way. Small steel pinch bowls available at kitchen supply. The nice thing is they're eminently reusable as compared to these foil cups, which are difficult to wash and recycle. Analytical balances can be quite prohibitive. Again, depending on the outcome that you need, a jeweler's scale may be able to provide you the information you need. And if you needed to get a desiccator, maybe measuring moisture content is difficult because you're somewhere with a high level of relative humidity. You can find silica desiccant quite available at many shipping organizations, mailing centers or post offices, and put it into a sealable plastic tub with a lid, and it can become a useful desiccator. Just put a metal rack in so that your hot samples coming out of the oven do not contact with the silica. The nice thing about silica too is you can recharge it. You can in many cases after you've used it for several samples, the silica loses its efficacy. You can just put it into, again, a low oven, approximately 100 degrees Celsius, and rack it out, and it will recharge with that low heating. The moisture will be driven off of it. Some samples are just more difficult to deal with, and we'll address some of the challenges here. The smaller you can make the particles in your food product, the easier it's going to dry, and the faster it's going to dry, saving you energy and time. The challenge is, for some food products, you have to grind it using some sort of mechanical grinding, coffee grinder, a ball mill, and grinding heats up the sample and you're going to lose moisture during that process. So you may need to manually chop some products or chop it in a way that's going to keep the product cold. In some foods, moisture migration becomes problematic. I think of a project I worked on with a frozen pizza where there was moisture migration across the different toppings, and it was very tempting to just say, well, let's measure the moisture of the total pizza. What we really needed to worry about was the moisture content of each of the individual components to identify water activity and moisture content and identify strategies to rectify the moisture migration. Composite foods just problematic across the board. Feel free to ask me questions if you got issues. Humectant samples. Some foods just suck moisture out of the air, and the chemistry of those foods becomes problematic. And so this is where you do need to be aware of the temperature being used for the heating process, and you want to be using a well-charged desiccator to stabilize those samples, and then moving very quickly in an environment where the relative humidity is being controlled well. Some samples, as we mentioned with the Carl Fisher unit, have high colligative properties and bound water, which make it difficult to be able to accurately measure the moisture content. And these are samples that may be more amenable to Carl Fisher type measurements. Last but not least, in some food products, as you're drying them, there will be what's called case hardening, where the outside dries really quick and a crust forms around the product that slows down the moisture migration from the inside of the particle. And again, the smaller you grind a product, the better you're going to have mass transfer and the less likely you're going to have case hardening. But this is something to be aware of. So moisture content, it's easy to measure. It can be done with some basic lab equipment. You now can do it. You can do the math as well. Take care and we'll talk soon.